For decades, scientists were certain the Big Bang marked the absolute beginning of time, space, and everything that exists. But new data from the James Webb Space Telescope is telling a different story. It has found galaxies that are too old, too large, and too well-formed to fit within the timeline we thought we knew. If what Webb observed holds up, the universe may have been building itself long before anyone imagined. This is the discovery that is rewriting our understanding of how the cosmos came to be. When the James Webb Space Telescope began full scientific operations in mid-2022, astronomers were expecting confirmation of what they already believed, not a confrontation with everything they had built. The mission seemed clear. Look back to the universe's first few 100 million years and watch the earliest galaxies emerge from darkness. Webb was built unlike any telescope before it. Its gold-plated primary mirror, 6.5 meters across and made of 18 precisely aligned segments, collects more than 6 times the light of the Hubble Space Telescope. The observatory sits roughly 1.5 million kilometers from Earth at a gravitationally stable position called L2, far from the warmth and light interference of our planet. From that fixed point, its instruments remain chilled to below -230 degrees Celsius, sensitive enough to detect the faint infrared glow of the very first stars, whose light has been stretched across billions of years of cosmic expansion. Because light travels at a finite speed, about 300,000 kilometers per second, every additional light year of distance represents another year back in time. A telescope tuned to faint infrared light is, in effect, a time machine. The farther it looks, the earlier the universe it reveals. By capturing wavelengths invisible to the human eye, Webb peers more than 13 billion years into the past, approaching the moment when the first atoms condensed into stars and galaxies. According to the Standard Model of Cosmology, the universe began roughly 13.8 billion years ago, in an extraordinarily hot, dense state that has been expanding and cooling ever since. About 380,000 years after that beginning, the first atoms formed, and a brilliant fog of plasma thinned, releasing what we now call the cosmic microwave background, a faint afterglow still detectable today. What followed was a long, starless interval known as the cosmic dark ages, filled only with hydrogen and helium gas slowly drifting through space. Gravity gradually pulled that matter together until the first stars ignited around 200 million years after the origin. Clusters of those stars merged into larger systems, and by 1 billion years after the beginning, mature galaxies were expected to exist in significant numbers. The deepest images from Hubble supported that picture. Webb was designed to fill in the missing stages in between. Instead, its very first data forced scientists to rethink everything. In a patch of sky, no larger than a grain of sand held at arm's length, a region chosen precisely because it appeared nearly empty, Webb's first deep field image revealed thousands of galaxies packed together like glowing embers in the dark. Some were chaotic and blurred, which matched expectations for young, forming systems. But others appeared bright, compact, and astonishingly massive. Their light had traveled more than 13 billion years, showing us a universe only a few 100 million years old. That level of structure and organization should have been impossible so soon after the first expansion. Simulations based on the Lambda CDM model, Lambda Cold Dark Matter, predict that galaxies of comparable size need nearly 1 billion years to grow. What Webb found was far ahead of schedule. One of the most striking examples came from a Webb survey known as GLASS, the Grism Lens Amplified Survey from space. It uncovered a compact system called GLASS-Z13, whose light began its journey around 13.5 billion years ago. Webb captured it as it appeared roughly 320 million years after the universe's birth, yet it already looked mature and luminous, possibly containing billions of stars. Shortly afterward, another candidate, CEERS-93316, emerged from a separate observing program dating to roughly 240 million years after the first expansion. Even if later refinements adjust those numbers slightly, the pattern remains unmistakable. Galaxies were forming at a pace that defies existing theory. To understand how extraordinary that is, consider how galaxies are actually built. The first generation of massive, short-lived stars, known as population 3 stars, formed entirely from hydrogen and helium. When they exploded as supernovae, they seeded the surrounding gas with heavier elements. Those metals allowed gas to cool more efficiently, collapse into new stars, and enable the earliest galactic structures to take shape. But these cycles take time. Each generation must live, die, and recycle its material before the next can begin. Seeing chemically enriched, well-organized galaxies when the universe was still in its infancy implies that several generations of stars had already come and gone in rapid succession. Webb's near-infrared spectrograph confirmed traces of oxygen, neon, and even carbon, elements that can only exist after multiple stellar lifetimes. The evidence pointed to a cosmos that achieved complexity far earlier than expected. Initially, some astronomers questioned whether Webb might be misled. Could these bright objects be closer galaxies, reddened by dust, only appearing ancient? Could gravitational lensing, light bent and amplified by intervening galaxy clusters, be making ordinary galaxies look extraordinary? Teams around the world rechecked the data using independent methods and calibration pipelines. When the distinctive hydrogen emission lines were measured precisely, several of the targets proved undeniably ancient, more than 13 billion light-years away. The most distant confirmed system found so far lies roughly 33 billion light-years from us in today's expanded universe, meaning we see it as it was just 330 million years after the first light of creation. More examples almost certainly await detection as Webb continues scanning deeper. If galaxies of that mass already existed so early, something in our understanding of cosmic growth is incomplete. The current model assumes that dark matter, the invisible substance making up roughly 85% of all matter, served as the gravitational framework on which ordinary gas condensed. Perhaps dark matter interacted more strongly, or formed dense clumps sooner than expected. Another possibility is that early gas clouds cooled and collapsed with astonishing efficiency, converting much of their mass directly into stars. Webb's early data suggests star formation rates up to 100 times greater than those seen in the Milky Way today. So intense that whole galaxies might have flared briefly like fireworks before settling into calmer states. Even with these adjustments, the numbers remain challenging. Simulations must boost both the rate of matter collapse and the conversion of gas into stars by factors of 10 or more to reproduce what Webb observes. The simplest interpretation is that structure formed faster than predicted. The more radical idea is that our timeline itself may need revision. If the early rate of cosmic expansion differed even slightly from modern estimates, the link between distance and time would shift. But even generous corrections cannot close the gap entirely. Something fundamental appears to be missing from our equations of the early cosmos. Webb's findings also compress the era of reionization, the transformation when ultraviolet light from the first stars stripped electrons from hydrogen atoms and made space transparent. Before Webb, this process was thought to unfold between 500 and 900 million years after the universe's birth. Now, with luminous galaxies shining much earlier, the process appears to have begun as soon as 250 million years after the first expansion, leaving a remarkably short window between darkness and light. The cosmic dawn seems to have been less a gentle sunrise and more a sudden explosion of illumination. Webb sensitivity also revealed another puzzle. Evidence for supermassive black holes already in place at these early epochs. Some of the compact, radiant sources Webb detects may host central black holes millions or even billions of times the mass of the Sun. Growing such enormous objects in only a few 100 million years demands either extreme feeding of surrounding gas or the direct collapse of immense primordial clouds, processes that strain the limits of modern astrophysics. Understanding how these ancient giants formed has become one of Webb's defining scientific objectives. To verify this emerging picture, astronomers are extending Webb's deep field campaigns and launching specialized programs such as Cosmos Webb, JADES Deep, and Primer. These surveys will map immense regions of sky, tracing how the first galaxies clustered, merged, and evolved. At the same time, theorists are re-examining assumptions about dark matter, gas cooling, and cosmic expansion, building new simulations to test each possibility. As more Webb data came in, the pattern became undeniable. Independent research teams confirmed that the early universe contained far more large, bright galaxies than expected. Even after reanalyzing some that turned out to be closer than first thought, many remained astonishingly ancient. The statistics revealed that massive galaxies were 10 to 100 times more common in the young universe than any model had forecast, a discrepancy that cannot be dismissed as observational error. Simulations still cannot reproduce that speed of growth. Even when scientists raise star formation efficiency in their models, the galaxies remain too faint. To match Webb's data, gas clouds would have to collapse with near-perfect efficiency, converting most of their mass directly into stars, something no known physical process achieves. Some researchers suspect the key may lie in dark matter itself. In conventional simulations, it behaves like a cold, passive scaffolding that slowly gathers normal matter through gravity alone. But the galaxies Webb sees appear too quickly formed for that slow process. Some physicists now explore models where dark matter is self-interacting, able to nudge and collide with itself, forming dense clumps that draw in gas far faster. Others favor what is called fuzzy dark matter, whose particles are so light and wave-like that they blur together, creating quantum pressure that subtly alters how structures grow. A few speculate that dark matter may have had temporary interactions with radiation in the young universe, triggering earlier gravitational collapse. Each of these ideas demands changes to particle physics, and each would make the early universe far more dynamic than the quiet framework described in textbooks. Another possible key lies in the initial conditions of the cosmos. During the burst of inflation that expanded space in the first fractions of a second, tiny quantum fluctuations were stretched to cosmic scales. If those ripples were stronger or more uneven than assumed, matter could have gathered almost instantly into deep gravitational wells. New inflationary models, some inspired by string theory, others by quantum field interactions, predict exactly that. A rougher, lumpier beginning that would make Webb's early galaxies inevitable rather than anomalous. Then there are primordial black holes, theoretical relics of extreme density fluctuations that may have formed before the first atoms existed. If even a small population of these objects emerged, they could have acted as seeds for galaxies, attracting gas and triggering cascades of star formation. Their gravitational pull would have heated infalling material, producing radiation bright enough for Webb to detect across billions of light years. Intriguingly, some of the compact, intensely luminous sources in Webb's deep field images show exactly the kind of spectral signatures expected from such objects. Detecting a clear conformation, perhaps a specific X-ray signature or a gravitational wave pattern, would be one of the most profound discoveries in the history of cosmology. Webb's spectroscopy is also opening a new window on early cosmic chemistry. In galaxies less than 500 million years old, astronomers are already finding the spectral imprints of oxygen, nitrogen, magnesium, and even hints of silicon. Such elements can only exist after multiple generations of massive stars have lived and died. This means the first stellar populations must have formed extraordinarily quickly, perhaps within 100 million years of the universe's origin. Some simulations suggest these earliest stars were supermassive, hundreds of times the mass of the Sun, burning furiously and collapsing into black holes after only a few million years. Their explosions would have flooded nearby gas with heavy elements, enabling the next generation of stars to form at breathtaking speed. Others envision violent mergers between nascent galaxies where colliding gas clouds compressed and ignited intense bursts of star formation. Either scenario paints the young cosmos as a place of chaos and creation happening simultaneously, a cosmic furnace rather than a gentle dawn. Equally transformative is Webb's evidence for a deep connection between galaxies and supermassive black holes. In the modern universe, black holes grow at the hearts of mature galaxies over billions of years. But Webb is showing that this relationship may have begun far earlier. Some young galaxies already contain central black holes, millions or billions of times the Sun's mass. The radiation from these active centers could have stirred, compressed, and regulated surrounding gas, directly influencing how stars formed. In this feedback loop, galaxies and their central black holes evolved together, an intimate partnership that may have shaped the entire cosmic landscape. These clues also ripple outward to challenge our understanding of dark energy, the mysterious force accelerating the expansion of space. If structures formed earlier and faster than expected, perhaps the balance between gravity and expansion was different in the past. Some cosmologists propose that dark energy strength has changed over time, starting weak and growing stronger only after the universe reached a certain age. Others think the geometry of space itself may not be perfectly uniform, and that subtle curvature could alter our measurements of distance and time. Webb's ongoing surveys, which chart how galaxies cluster across different epochs, could reveal whether dark energy is truly constant or an evolving phenomenon. Beyond that lies the most elusive question of all. What was time itself like at the very beginning? Near the universe's origin, the known laws of physics merge into a domain where quantum mechanics and gravity coexist. Some theorists propose that time flowed differently in the universe's first moments than it does now. Under those conditions, what we measure as 300 million years could have passed in a fraction of that duration, according to the universe's own internal clock. Others go further, suggesting our universe may have bounced from a previous one, that an earlier cosmos collapsed under its own gravity, compressed to a state of maximum density, and then rebounded, leaving faint imprints that became the galaxies Webb now observes. If any trace of such a pre-existing cycle were found in Webb's data, it would fundamentally change our definition of a cosmic beginning. To explore these frontiers, astronomers are developing an entirely new generation of analytical tools. Sophisticated algorithms now trace every photon recorded by Webb, reconstructing the path of light across expanding space to infer how galaxies evolved chemically and dynamically. Machine learning systems compare thousands of simulated universes against real observations, searching for which physical laws best reproduce what Webb sees. On the theoretical side, cosmologists are blending quantum gravity mathematics with large-scale simulations, attempting to bridge the gap between the smallest particles and the largest structures in existence. Complementary observatories are joining the effort. Radio telescopes such as LOFAR in Europe and the upcoming Square Kilometre Array in Australia will map the faint 21-centimeter signal of neutral hydrogen, charting how the cosmic fog lifted during ionization. The CMB-S4 experiment in the United States will remeasure the ancient microwave background with unprecedented precision, checking whether its tiny irregularities match the galaxies Webb detects. Even gravitational wave detectors like LISA, scheduled for the 2030s, may pick up the background hum of primordial black holes or early mergers that helped shape the first galaxies. Each new instrument adds another piece to the puzzle. Webb may have provided the spark, but together these observatories could illuminate the full chain of cause and effect, from the universe's very first instant to the vast structures we inhabit today. The next generation of space observatories is preparing to carry this work forward. The Nancy Grace Roman Space Telescope, launching later this decade, will scan vast regions of sky to measure cosmic structure on a grand scale. The Habitable Worlds Observatory, still in its design phase, will extend Webb's legacy from distant galaxies to nearby exoplanets, studying worlds that orbit other suns in search of chemical signs of life. Further ahead, mission planners envision telescopes shaded by kilometer-wide light-blocking sails, capable of capturing even longer wavelengths from the first molecular clouds in history. While Webb peers outward, physicists are looking inward to the universe's hidden architecture. Experiments deep underground, such as those in South Dakota and Italy, are hunting for the elusive particles that may make up dark matter. Galaxy mapping projects are tracing how cosmic structure moves today, testing whether the laws of gravity themselves may evolve across cosmic time. Together, these efforts form a bridge between the largest and smallest scales, joining astrophysics with particle physics in the search for a single unified picture of reality. Webb's impact, however, reaches beyond laboratories and equations. It has reignited a question as old as humanity itself. Why is there structure at all? If the universe organized itself so swiftly, perhaps creation is not a rare accident. Perhaps it is simply what the cosmos naturally does. Some researchers are exploring the idea that complexity arises spontaneously whenever energy flows through matter, whether in galaxies, storms, or living cells. In that sense, the same principles that shaped the first stars may still echo in the chemistry of life and in human thought itself. Each photon Webb captures is a whisper from a time before there were eyes to see or minds to wonder. Those faint signals traveled billions of years to reach us, carrying memories of a cosmos that was young, hot, and brimming with possibility. When we study them, we are not just observing ancient galaxies, we are reading the preface to our own existence. The James Webb Space Telescope has done more than expand our vision. It has transformed how we think about time. In just a few years, it has shown that the infant cosmos was not a quiet nursery, but a storm of creation, where light, matter, and gravity work together in astonishing harmony. Each new discovery challenges the boundaries of what we thought possible, forcing science to rewrite its oldest stories. Whatever the final answers turn out to be, one truth already stands beyond dispute. The young universe was astonishingly alive. It was turbulent yet organized, chaotic yet creative, a place where gravity, radiation, and matter cooperated to build complexity almost overnight. The James Webb Space Telescope has not merely extended our vision into the past. It has opened a doorway into a realm where the familiar laws of nature begin to blur, reminding us that the story of creation is still being written, one photon at a time. For decades, scientists were certain